We move to section 3 in the prerequisite chapter on functions and their graphs. Now, you studied functions back in Algebra 1 and Algebra 2, probably more in Algebra 2 than in Algebra 1. And of course, we studied functions in pre-calculus. So again, this is in the prerequisite chapter because most of this should look really familiar. A relation between two sets x and y, notice the notation there for the sets x and y, is a set of ordered pairs, each in the form xy, where x is a member of set x and y is a member of set y. Any set of ordered pairs. No restriction. However, a function from x to y is a relation between x and y, but it has one additional property, one additional bit of criteria. That means that any two ordered pairs that have the same x value also have the same y value, which is a nice way of saying that you can't have the same x for more than one y. It has to have a unique y value. X is typically what we refer to as the independent variable, and y is the dependent variable. Now, a nice formal definition here says for a real valued function of the real variable, let x and y be the sets of numbers, a real valued function from f of a real variable x from x to y is the correspondence that assigns, I like that term, correspondence. That assigns to each number x exactly one number y, x coming from set x and y coming from set y. Now, the domain of your function, little notation here, is the set x. However, set y is not the range necessarily. It may be just a subset or part of the range that consists of the values that correspond. A number y is an image of x under f if it is denoted f of x. So the range would be consisted of all the images of the numbers from set x, from the domain. So that's where we usually remember the vertical line test. That's where we would use the vertical line test here. Now, this correspondence can be described a number of ways, usually with an equation, sometimes with a graph, sometimes with a description. So when we write them out as equations, the functions as equations, we like to have y in terms of x. When we have y in terms of x, we say that the function is defined explicitly, such as y equals 3x minus 1, or using function notation, f of x equals, 3x minus 7, or f of x equals 3x minus 7 written this way, because the y value is the same as the f of x. The f of x is just function notation, and it's a little bit better for some reason, for some circumstances, especially when you're evaluating the different values for x. Now, y equals 3x minus 7 can also be written as 3x minus y equals 7 by rewriting the terms. When the x's and the y's are on the same side and I don't have y in terms of x, then we say it's not defined explicitly, but it's defined implicitly. So a little different there. Function notation is best for functions that can be written explicitly, because then we can isolate the y. F of x would be the same as y. It would be your dependent variable. F is the name of the function, but f of x is the actual y value. And x, of course, is the independent variable. Also nice for evaluating, as I mentioned before. Here's an example. Given f of x is equal to x squared plus 15x. If I write this as y equals x squared plus 15x, and then it says find f of 2, which means find it when x is 2, I would get y equals 2 squared plus 15 times 2. I would get y equals, that'd be 4 plus 30 is 34. Now, if all I look at is this, I don't know what I plugged in for x to get this y value. However, if I use function notation, f of 2, which is 2 squared plus 15 times 2, is 34. So not only do I see what the y value is, I can see what the x was that this is the image of. So that's kind of nice. Also, it doesn't always have to have x as the independent variable. Usually we use x. We can also use t, which we do a lot when we're talking about time, t representing the independent variable that way. But f of x equals x squared plus 15x, and g of t equals t squared plus 15t. If they have the same domains, then they define the same exact function, just different variables. Let's consider this function, 3x squared plus 5x, and let's evaluate first in a f of negative 2. So I'm going to raise this up just a little bit here. F of negative 2 is going to be 3 times negative 2 squared plus 5 times negative 2. Use your order of operations. You do your exponent first. This is 4, so I have 12 plus negative 10, which is positive 2. So f of negative 2 is positive 2. For part B, I have f of a plus 2. Now f of a plus 2 means that you're substituting all of this in for the independent variable x. So f of a plus 2 would be 3 times a plus 2 to the second power plus 5 times a plus 2. It looks a little awkward to plug in something that's kind of like a binomial, but that's exactly what we do, and that's why we know how to do our algebra to simplify this expression. This is 3 times the quantity a squared plus 4a plus 4, and then over here plus 5a plus 10. So this is 3a to the second plus 12a plus 12 distributing plus 5a plus 10. And this would be 3a squared. We would like to simplify our answers when we can, plus 17a plus 22. And that's f of a plus 2. Now this third part here is called the difference quotient expression, and we use it quite a bit, and you'll see it again many times, especially when we get to the chapter on derivatives, which is, I believe, chapter 2. But in practice, we'll do some algebra with it first. So here we want to find, using this function f, we want to find f of x plus delta x minus f of x all over delta x. Now, to really do this, I'm going to need a few lines here, so I'm just going to put part C right here. And f of x plus delta x would be 3 times x plus delta x squared plus 5 times x plus delta x. Okay, that's this part right here. Minus f of x, which is this expression, 3x squared plus 5x, note the parentheses, all over delta x. Now, it might not look like this guy is going to simplify, but he actually simplifies halfway decent. Again, I have to do a little bit of algebra here in the numerator. I have 3 times, this would be x squared, plus 2x times delta x. I like to put parentheses around delta x if it's being multiplied or raised to a power, plus delta x squared. That's this part right here. Okay, and then I'm going to distribute here. I have plus 5x plus 5 times delta x. I hope I left myself enough space. And then here I'm going to have to write kind of small, minus 3x squared minus 5x. And that's all over delta x. So I simplify a little bit more by distributing up here. And I have 3x squared plus 6x times delta x plus 3 times delta x quantity squared plus 5x plus 5 times delta x minus 3x squared minus 5x. And that's all over delta x. Now you may be wondering, how is this going to simplify? Well, I have some like terms, and not only do I have like terms, but they're opposites. This is a 3x squared and a minus 3x squared. They cancel. This is a plus 5x and a minus 5x. They cancel. So every term in the numerator that did not have at least one factor of delta x canceled out. Nice. So I have this, and they all have at least one delta x. So all in one step, I'm going to factor out a delta x in the numerator. Gives me 6x plus 3 times delta x plus 5. I factored the delta x out of this, one out of this, and out of this, and that's all over delta x. Now you see why I factored it out, because now I can simplify it even further, and I get my difference quotient expression to simplify all the way down to 6x plus 3 times delta x plus 5. And there's the simplified form. Now, when you're dealing with functions and you're interested in analyzing them a little bit, one of the things, of course, that you want to be concerned about are the values that the independent variable can take on, or the domain of the function. Now, typically, the domain is implied. or is described implicitly. And what I mean by that is it's just assumed to be every number that makes sense when you plug it in. But sometimes, as in the first example, they may give you a restricted domain, and in this case they do. They say x can be 1, or x can be 2, or x can be 3. So that's referred to as an explicit description of the domain. An implicit description of the domain would be finding the set of all values that make sense, pretty much make sense, when you plug in for x. Now, with a square root, you can't have the square root of a negative, so you'd have to throw all those out of being possible values in the domain. It would have to be 0 and any positive numbers. So in interval notation, capital D there with the lowercase letter, like subscript f there, means the domain of the function f would be all positive numbers, all positive real numbers. All right, now, if they don't describe it by giving you a restricted domain, you assume it's the domain is the implied domain or the implicit domain, every value that makes sense. And in the next example, we have our first look at a multi-ruled function. The multi-ruled function, for the following multi-ruled function, more than one correspondence there, more than one mapping, if you want to say, we want to find its domain and we want to sketch the graph. Now, students sometimes struggle with multi-ruled, but you just have to remember it follows this rule for these values of x. It follows a different rule for these values of x. Now, I know that if I was to graph y equals x squared, I would get a parabola. And I would know that if I graphed y equals the square root of x, I get kind of a half of a sideway parabola, so to say, that goes through 0, 0. So in this case, if I was to graph everything for these x values, now remember, the domain, 1, 2, 3, 4, would be, for a parabola, would be all real numbers. And I would get something that would look like this. But we have a restriction for this rule. It's only those values of x that are less than 0. So I am going to have to get rid of all these for when x is greater than 0. And then for when x is equal to 0, I am going to have to put an open dot there to indicate that the graph stops there, but it does not contain that point. So I get kind of a half of a parabola like that. That's this part right here. Now, for the next part, I'll do this in a different colored pencil, if I can find my colored pencils. Oh, here's green. And in this case, for x greater than or equal to 0, so if I substitute 0 in, I get 0, so that kind of fills in that hole. If I plug in 1, I get 1. If I plug in 4, I get 2. And I get, as I mentioned before, what looks like kind of a half of a sideway parabola. And I get that as the entire graph, the whole thing. Now, you don't have to use colored pencils. I mean, it's okay if you do, you know, that helps you to keep everything straight. But the entire regular pencil and green pencil there, that makes up the graph. And its domain would be all real numbers, because there are no values that are skipped. You say, well, you can't have a negative here. It's defined only for the positive. So it would be from negative infinity to infinity. Right? Now, of the functions, one type of function is very special because, as we'll study later on, they have inverse functions. A function from x to y is said to be 1-to-1 if for each y value in the range there corresponds exactly one x value in the domain. Now, since it's a function, that means each x has exactly one y. If it's 1-to-1, each y has exactly one x. Now, the function y equals x squared, as I was kind of graphing before, I don't know if you can still see this here like that, it would have the same y value for two different x's. If I plug 2 in, I get 4. If I plug -2 in, I get 4. It is not considered a 1-to-1 function. You may or may not remember the horizontal line test to see if a function is 1-to-1. Well, if each y is only used once and each x is only used once, we have a 1-to-1 function, and therefore this type of a function has an inverse function. A function from x to y is onto, that's an expression you don't see very often, and we didn't see it in pre-calculus, if its range consists of all of the values from the set y. So if every y value is used, then we say that that function is on 2. For example, f of x is equal to 2x plus 1. The domain would be all real numbers. The range is all real numbers. So in that case, we would say that that would be an example where it's on 2. But it could be a you could have a restriction on your range there, depending on the function. Now, here's where it gets a little fancy, and this is something where you're going to have to draw upon your knowledge from your Algebra 2 and your pre-calculus days. It says, given one graph, we can create a family of graphs by transforming the graphs using vertical and horizontal shifts, vertical and horizontal dilations, and reflections. We can also throw in rotations, but to do that, we probably need a little bit more from our pre-calculus days and analytical geometry. And it's not as big, as highly emphasized as it once was, and you'll see this later on in, say, like a Calc 2 class where they might, or a Calc 3 class where they might do a rotation. I'll kind of explain it then. So we can have a family of graphs. It's called a family because typically families have some type of common characteristic. There was a family in my hometown. There was like 6 or 7 kids. You could tell every one of those kids was from the same family because of their eyes. They all had the same exact looking eyes. And it's hard for me to explain them. I don't have a picture of them, but you could tell that they were one of the Greens from their eyes. I went to school with a guy who married one of the Greens, and that's how I know that family a little bit anyway. So what kind of graphs are we concerned about? Well, we're concerned about the types of graphs that you would probably study in pre-calculus. So I have some of them right here. We have the constant, the linear, of course they don't have the arrows, shame on them. Absolute value, one of my favorite is the greatest integer. Now they use just brackets, but I like to use kind of double brackets like this, and I believe this is what our textbook uses there. We have a quadratic, cubic, square root, cube root, exponential, logarithmic, now that's second semester stuff a little bit more, reciprocals and rationals, and then the trig ones as well. We'll do a little review of trig in the next section. So those are all the basic parent functions, and then you can make these graphs stretched, shrunk, shifted, right, left, or translated right, left, upward, downward. You can reflect them in the x-axis, reflect them in the y-axis, reflect them pretty much in any line that you choose, but those are the two that we use most often. And those are also going to give us variations of the parent, but it's going to still be the same parent function. If we have an absolute value, notice the V shape. A reflection might make it look like an inverted V. A stretch or a shrink might make it look like a skinny V or a wide V. And if we shift it right, left, up, down, you still have the same V shape. So you have that basic common characteristic. These are guys that you should know how to graph, because they're going to ask you to graph from these graphs of equations that have the different types of transformations. All right. The elementary functions, some of which I had for the graphs there, are the algebraic functions such as your polynomial, your radical, your rational, trig functions, exponential, and logarithmic functions. And of all those, probably the polynomial functions are the most common, or the ones that you're probably most used to anyway. Probably in some ways a little bit even some of the more elementary ones, not wanting to play a pun on the name. But polynomial functions can be thought of as any function that can be written in the form a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus all the way down to a sub 2 x squared plus a sub 1 x, which would be like x to the first, plus a sub 0, and that's your constant term. It'd be like x to the 0, which of course is 1. These polynomial functions, the exponent for the variable is referred to, the highest exponent, the largest one, is referred to as the degree. So in this case, this is degree n. The coefficients are those constants that are being multiplied all the way through. A sub n is sometimes referred to as the lead coefficient, and of course a sub 0, since the variable is not there, is referred to as a constant term. If the degree is 0, for example, if you have f of x equal 5, that's a constant function. Remember the graph just a little bit ago? We talked about constants. Oops, I've already lost my parent graphs. Oh, there it is. The constant one was the very first one. All right. Then you have linear. That's degree 1, so that might look like g of x is equal to 3x plus 7. See, degree 1 right there, and that, of course, has to do with the linear there. That's the second guy. Okay. And then quadratic functions, that's degree 2. H of x is equal to maybe x squared plus 3x minus 1. That's a graph that we've already done a couple of examples of where we had a parabola. This is called a quadratic function. Now you may wonder, well, 0 constant, 1 linear, a line is one-dimensional. Quad, that would mean 4. Well, it's because in the old days, squares, which are two-dimensional shapes, degree 2, used to be called quadrangles because of the 4 right angles. A cubic function, k of x, might be something like 3x to the third minus 2x squared plus 1. As an example, it's degree 3. So usually we use this terminology. It should become familiar. Now once we get past degree 3, you guys may not be as aware of degree 4 being quartic, degree 5 being quintic, and so on up the line. There's names for all of them, but in general we say if it's degree n, it's a polynomial function of degree n. Okay? A rational function is essentially a ratio of two polynomial functions. It has the form f of x equals p of x over q of x, where q of x can't be 0 because you can't divide by 0, and p of x and q of x are polynomials. Definition: an algebraic function of x is a function that can be expressed as a finite number of sums, like I had up here, sums and differences, multiples, quotients, like I have right here, and radicals that involve x. Functions that are not algebraic are referred to as transcendental. There's a good word for you. There is a whole algebra of functions that involve operations, identities, inverses, and closure. Right now, we're used to having more of an algebra of along the lines of numbers, where we can add numbers, subtract numbers, multiply, divide. We have an identity. We have an inverse for both addition and for multiplication. And of course, we have closure. When you add two real numbers, you get a real number. When you multiply two real numbers, you get a real number. But when we're talking about functions, we're talking about adding functions, subtracting functions, multiplying functions, dividing functions. We have an identity function. The identity function typically is thought of as f of x equaling x, because whatever you plug in, you get exactly right back. Sometimes they'll even call it I of x for identity. Inverse functions, I've mentioned that before. And then, of course, closure, meaning that when you combine functions, you get a function. There is another way, besides adding, subtracting, multiplying, and dividing, to combine functions, and that's using the operation of what we call composition, or to compose functions. So let's scoot right over here. Okay. Composite functions. Let f and g be functions. The function given by f circle g of x is equal to f of g of x. Notice that the one closest to the variable here in this notation is the one that's in the interior, in the inner function, so to say, f of g of x, and that's how it's pronounced. It's read f of g of x, not f times g of x. F of g of x is called the composite of f with g. Sometimes we say f composite g, sometimes we just say f circle g. The domain of the composite function is the set of all values in x which are in the domain of g, the inner function, whose images, the y values, are also in the domain of f. So it's kind of like cutting out the middleman. If we have three sets here and we take x from the first set, the domain of g, and we map it to g of x, this is the rule here for g, then we get a value that's now in the domain of f, which was equal to the range of g here, and we set that and send that over here to using the outer function f of g of x. Or you can do it all in one step by using the composition. I'm going to show a couple of examples here. Let f of x equal 4x minus 3, and let g of x equal x squared. Find f circle g and g circle f. Now, this is what I've done is I've changed the order. This is the outer function, this is the inner, this is the outer function, this is the inner. I've changed the order, which makes me think of commutativity. But are these functions commutative? Is the operation of composition a commutative one? Well, Let's find out. F circle g of x, at least with this example, let's find out, is f of g of x, which is f of, now g of x is x squared, so I replace the g of x with x squared, and now I plug this in for my rule here, and I have 4x squared minus 3. That's the first guy. G circle f of x is g of f of x, which is g of 4x minus 3. Notice how I replaced the f of x with 4x minus 3, and then I take g of that. So I'm going to plug all of this into the rule for g, and I get 4x minus 3 quantity squared. Is that the same thing? Well, no, because if you go ahead and multiply this out, you would get 16x squared minus 24x plus 9 after you get done squaring that out. So you can see they're very different. So are they commutative? No. There's another couple of examples. Throw in a trig one. Now we're going to do a lot more trig and review of trig in the next section. But we had this not that long ago, back in pre-calculus, so we can probably deal with it a little bit. F of x is equal to 3x plus 1, and g of x is equal to the sine of x. So f circle g of x is equal to f of g of x, which is equal to f of the sine of x, which is equal to, now I'm going to plug the sine of x in for the variable, so I get 3 times the sine of x plus 1. On the other hand, g circle f of x is equal to g of f of x, which is equal to g of f of x being 3x plus 1. And then g of this, I get so lazy sometimes, just want to scratch it out. There we go. I'm going to plug 3x plus 1 into the rule for g right there, in for the variable. So I have the sine of 3x plus 1. And no, these are not the same. Now, we talked about x-intercepts. In terms of functions, this has an x-intercept. The x-intercept is the ordered pair 2, 0. If you plug 2 in for x, you get 0 for the y value. So we say that 2, 0 is the x-intercept, but corresponding to that, we say 2 is the 0 of the function f. A 0 would be those values that when you plug in for the variable x, it makes the expression f of x equal to 0. So the zeros of function f are the solutions of the equation f of x equals 0. You're going to hopefully remember that from previous years. We have just a little bit more having to do with symmetry, and then we'll finish this up. We have already considered symmetry of the function of an equation in x and y. In function terminology, when we have functions, we like to talk about functions that are even functions and functions that are odd functions. A function is even if its graph is symmetric to the y-axis. A function is odd if its graph is symmetric to the origin. Now remember, if it's symmetric to the x-axis, it's not a function. So the test for even and odd functions, very similar to what we had before, to find if something's symmetric to the y-axis. Remember how we plugged in the opposite of x and we get back to the original? We plug in the opposite of x, we get back to the original. For an odd function, we plug in the opposite of x in for x, the opposite of y in for y, and that means f of the opposite of x. If we plug in the opposite of x in for x, we get the opposite of y for the y. So it's equal to opposite of f of x. I would remember this. You're going to see that terminology and be able to use that. Determine whether the function is odd, even, or neither. F of the opposite of x is equal to the opposite of x cubed plus the opposite of x. So the opposite of x times the opposite of x times the opposite of x is the opposite of x to the third minus x, which is, if I factor out a negative 1, x to the third plus x. And notice here that this is equal to the opposite of f of x. So therefore, this is odd, symmetric to the origin. If I go about and do the trig ones, we're going to have to pull back on our memory for trig, because there's a step here that we're going to plug in. F of the opposite of x is the cosine of the opposite of x. Now, here's the trick. Back in trig, they talked about even and odd functions. Cosine is an even function. So is secant. It's reciprocal. The other four, sine, tangent, cosecant, and cotangent, are all odd functions. So this one is even. Lots of stuff to remember from your pre-calc days. For part C here, h of the opposite of x is equal to the opposite of x squared plus the opposite of x plus 1, which is x squared minus x plus 1. Now, there's nothing I can do to make this get back to the original because only one term has a different sign, and I can't multiply through by -1 to get the opposite, or factor out a -1 to get to here because the signs are different. So in this case, this one is neither. So lots of practice here, and that will lead you into the last section of the prerequisite chapter. Now, I don't have a video that I created specifically for that because the section in the book actually doesn't spend very much time reviewing trigonometry, logarithms, exponentials. However, I have made it available in the class that you can get to my catalog of videos for pre-calculus. Primarily, the logarithms and exponentials would be in the chapter 3. The trig would be in chapters 4, 5, and 6, so if you need to do some review. I also have found a video that's a little bit shorter than going through literally dozens of videos that I have that's a little bit more specific and does a relatively decent job reviewing the key topics that you need to know going into chapter 1 when we actually start the pure calculus of the class. So practice, 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 and of course if unsure, be sure to ask questions.